Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 19, 2016. In this video lecture, we're going to focus on the aerodynamic drag of an airplane and the required power needed to overcome that drag while in flight. Aerodynamic drag is defined as the force opposing the thrust force and motion of an aircraft, vehicle, or object that moves through the air. In regards to the aerodynamic drag of an airplane, there are several different types of drag, including induced drag, parasite drag, skin friction drag, form drag, also known as pressure drag, interference drag, trim drag, profile drag, cooling drag, and wave drag. In this video lecture, we will only cover the calculation regarding induced drag and zero lift form drag. Aerodynamic drag calculations can become extremely complicated. However, they are easily calculated by accessing something called the lift over drag ratio, which we'll be covering in a few minutes here. Induced drag is a function of the lift of the airplane during a climb. The induced drag force in pounds is calculated by accessing a given airplane's lift to drag ratio, or L over D, for the given amount of lift at a certain airspeed. Form drag, especially during zero lift steady cruise flight speed, is in reference to the airplane's projected frontal area, wetted area, and applicable drag coefficients for both the given airplane, represented by the formula pounds drag D is equal to the drag coefficient times the air density in slugs per cubic feet times the reference area times the airspeed quantity squared, this quantity then divided by 2. Using this formula can become very tedious and complicated because you have to break up the reference area in both frontal and wetted area, and then the drag coefficients in both frontal projected frontal area and wetted area as well. So there's an easier way to make this calculation, focusing on the various L over D constants given for the airplane at different flight speeds, altitudes, and lifts. Form drag is especially dependent on the inherent 3D shape of the object moving through the air. Therefore, certain 3D shapes in regards to form drag also have typical drag coefficients. This is applicable to not just airplanes or aircraft, but any 3D structure that moves through the medium of air. So here we have common typical shapes and their measured drag coefficients. The four force vectors acting on an airplane while in flight are thrust, drag, lift, and weight. Drag and thrust oppose each other, as does lift and weight. We'll be focusing on the Cessna 172 Skyhawk airplane. In this case, it's at a rate of climb of 689 feet per minute, right at takeoff as it leaves the runway, with a takeoff weight of 2,200 pounds, a takeoff airspeed of 90 miles per hour, assuming no headwind, and the L over D for this flight parameter is 10.7 to 1. Let's calculate the drag incurred upon this 2,200 pound airplane when at takeoff rate of climb of 689 feet per minute. (689 feet per minute divided by 60 seconds translates to 11.48 feet per second climb. The airplane has already canceled out the weight of the airplane, 2,200 pounds, overcoming the acceleration of gravity times the mass of the airplane, which is the weight. The airplane is climbing at a greater lift than the weight of the airplane at a rate of 11.48 feet per second. The airplane's wings are developing aerodynamic lift greater than the weight of the airplane. The next step is to calculate how much aerodynamic wing lift is taking place to sustain an 11.48 feet per second climb. We know that force is mass times acceleration. The initial climb rate of 11.48 feet per second is a change in vertical speed, and thus is an acceleration. However, at a constant climb rate of 11.48 feet per second, the acceleration is 0, since there is no change in speed. the initial acceleration of 11.48 feet per second taken over approximately 1 second can be used to determine the initial aerodynamic lift force developed by the airplane's wings. The mass in this case is 1,000 kilograms, which is 2,200 pounds divided by 2.2. The acceleration, since it's 11.48 feet per second, change in speed over 1 second, the initial lift acceleration above weight or gravity would be 11.48 feet per second squared. So if we convert that into meters per second, we get 3.5 meters per second squared. Climb acceleration plus gravitational acceleration of 9.8 meters per second squared. So when we add the total acceleration involved, including overcoming gravity, times the mass, that's a total lift force of 13,300 newtons. 1 pound of force is equal to 4.45 newtons, so when divided out, that's 2,988.8 pounds of total lift. When this 2,200 pound airplane is climbing at the rate of 11.48 feet per second, its wings are developing 2,988.8 pounds of lift. Now we can calculate how much induced drag in pounds is incurred upon this airplane when at the given climb rate based on the L over D for the given airspeed. In this case it's 10.7 to 1, so we divide the amount of total lift into 10.7. During this climb, 279.3 pounds of drag upon the airplane is incurred. Drag opposes thrust, and the engine must develop enough power to overcome this drag before it can negotiate the given climb rate of 11.48 feet per second. As for the zero lift form drag, the given airplane, including the propeller, during level cruise flight, this can become complicated to calculate using the pounds drag formula listed previously, since both wetted surface area as well as projected frontal area drag both involving several different computations. Several different computations are required, including the wetted surface area and the projected frontal area and their applicable drag coefficient. So, in other words, it gets kind of complicated to use that formula. But, however, the easiest and fastest way to calculate the approximate zero lift form drag is to access the L over D for the given airplane's flight speed and altitude as per the manufacturer's specifications. Let's assume the airplane is flying at 5,000 feet above sea level at a speed of 120 miles per hour. The L over D listed for this altitude and flight speed is 8.3 to 1. Also assume that 7 pounds of fuel have been consumed by the time the airplane levels off to this altitude and cruise flight speed. So we subtract 7 pounds from the takeoff weight, we're left with 2,193 pounds. The airplane at this given point in time now weighs 2,193 pounds. The aerodynamic lift of the wings at level cruise flight is equal to the weight of the airplane, or 2,193 pounds. The L over D at this altitude and flight speed again is 8.3 to 1, so we divide the weight of 2,193, which is equal to the lift, into 8.3. So at this point, at this flight parameter, there's 264.2 pounds of drag. So when the airplane is at cruise level flight speed of 120 miles per hour at an altitude, the approximate drag incurred upon the airplane is 264.2 pounds drag. Since drag opposes thrust and the propeller's net thrust is equal to the drag during steady cruise flight speed, the propeller net thrust equals 264.2 pounds of net thrust. The power in watts to overcome aerodynamic drag is represented by the formula below. It's easier to use the D times V formula. Notice that the second formula is the same as the pounds drag formula, except that the airspeed V component is cubed, not squared. The first formula is the easiest and most practical to use since the pounds drag is already known, so this formula will be used to calculate the power required to overcome the aerodynamic drag involved. So the power to overcome the drag d times v is the feet per second airspeed of the plane times the pounds drag. So we convert 120 miles per hour to feet per second, 176 feet per second. So we multiply that times the drag incurred. It will cost 46,499.2 watts of power, then divided by 746, the number of watts to 1 horsepower, 62.3 brake horsepower. At this given steady cruise flight and altitude, the airplane's engine will have to transmit 62.3 brake horsepower of effective power to the propeller. As for the climb at takeoff of 11.48 feet per second and a climb drag of 279.3 pounds, the lift itself is quote-unquote paid for by the drag. So to know how much power is required for this particular climb at 90 miles per hour or 132 feet per second with an L over D of 10.7 to 1, simply multiply the flight speed times the pounds drag, and that translates to 828 watts. And when converted to brake horsepower, that's 49.4 brake horsepower. During the 11.48 feet per second climb, the speed is lower, 90 miles per hour, and the L over D is higher, 10.7 to 1, compared to the cruise speed, 120 miles per hour, and lower L over D, 8.3 to 1. This means that at takeoff initial climb, the minimum brake horsepower required is actually somewhat less than when at higher speed cruise flight in this particular case. But let's say the 5,000 feet cruise flight speed was reduced to just 90 miles per hour instead of 120, with an airplane weight of 2193 and an L over D of 8.3 to 1, then the effective brake horsepower requirement transmitted to the propeller would equal 2193 pounds divided by 8.3, so 264.2 pounds of drag. We convert 90 miles per hour to feet per second, 132 feet per second. And so when we multiply the two out, then divide it by 746, it will cost 46.75 brake horsepower to the propeller if the plane was flying at 90 miles per hour at the same level cruise flight altitude of 5,000 feet. The L over D is based on extremely complex computations established by aerospace engineers. However, the L over D specification listed at the given altitude, flight speed, and aerodynamic lift of the wing can provide a simple way to calculate the aerodynamic drag at a given flight speed, pounds lift, and altitude specified by the given airplane manufacturer. This power requirement is only applicable to steady flight speed, altitude, and lift in accordance to the given L over D, and does not include the higher power requirements needed for acceleration. If this plane was to accelerate from rest to 90 miles per hour in 12 seconds, the power required to do so at 2,200 pounds takeoff weight would approximately equal the formula power in watts for acceleration is mv squared divided by 2t. So the m in kilograms, 2,200 divided by 2.2, times the v in meters per second, so feet per second divided by 3.28 quantity squared, divided by an acceleration time of 12 seconds times 2. So when you work it out, that's 67,482.2 watts, which equals 90.45 horsepower, brake horsepower to the propeller. Of course, much more power is required at initial takeoff due to the fact acceleration is involved. But when the airplane rotates into liftoff at 90 miles per hour with 11.48 feet per second climb, 49.4 brake horsepower of 90.45 brake horsepower will be used to overcome the given climb drag, while 2,988.8 pounds of wing lift is developed. The L over D values for a given airplane are invaluable for quickly making aerodynamic drag calculations for a given airplane based off lift, speed, and altitude. Once the drag is known in pounds, this is simply multiplied times the flight speed in feet per second to obtain the power in watts required to overcome the given drag, and of course 746 watts is equal to 1 horsepower. So always look for the L over D values for the given airplane flight parameter setting, and then establishing the aerodynamic drag and the power required to overcome it becomes a much easier task. Thanks for watching this video, and